हेलो। everyone. Am I audible? Okay, I think I am. Yes. So, welcome to today's session, the live interaction session for week 9. So, I think probably we can wait for 2 minutes and begin. All right. So, let's begin. So, I believe in this week's lectures, we would have gone through something called data center networks. Data center networks. The whole this week and next week would also be possible. The next week, I mean week 10, would also be about data center networking. And you would be wondering what is so different with data center network that we have to talk about it specifically in a different whole set of lectures, right? So probably today we'll go through some motivation as to why data center networks came into effect and what is so special about data center networks. And basically, to be honest, in today's world, data center networks are what make the internet interesting. Make the internet interesting. Without these complex mechanisms, you would not be able to get data served to you at the rate at which it's being done right now. Every day you are uploading so many videos to YouTube. Like I myself will be uploading this video, and imagine where all this data goes and how they are able to retrieve this data at a very short time scale. Right? And the best aspect of this is scaling. It's scaling well as well. So every day, if so much info data is being added, so it is also scaling to accommodate all this data. How is it placed in the data center network? Is it placed like this as a row of servers, or is it something else? We'll take a look. Right. So as usual, this is Harish. I'm from IIT Hyderabad. This week 9 live interactive session, and of course the interactive session is to solve problems, previous year problems. And while we look at the problems, we'll also try and understand the theory behind it at a in simple words. So that's something that's the value that I would like to add to these sessions. Of course, it is expected that you will have networks background, meaning that you have done some lower course in networks, introduction to computer networks or something like that. But in case you have not, in case you've decided to jump directly into advanced computer networks, then probably this session might help you in understanding certain basic aspects that usually is skipped in the interest of time. Right? So when we move forward now, so and of course, so what I do every week is tend to so I tend to go through all the questions in the beginning, note down certain keywords, and then take it forward from there. All right, just to give you the idea of what we're going to look at in this. So so the following is not a typical component of a data center network. Right? Of course, we have DC being said here. DC is nothing but data center network. Right? Is it server? Is it network, storage, or is it workstations? I think the answer should be quite obvious here, but let's look at the answers at the end. Right? So what is the total number of servers supported by 4-port switches in leaf spine topology? Right? So leaf spine topology. Right? And 4-port switches. Basically, if a switch has 4 ports, then each switch in the topology has 4 ports, then how many servers can be supported? Right? So if you would have gone through the lectures this week, you might have come across a formula with which you will be able to answer this question. A straightforward question, right? So which of the following statements are correct about fat tree topology? Fat tree topology. Right? So there is something called bisection bandwidth. And right, so I'm just noting these keywords down. So which of the following statements are correct about modular data centers? We won't go too much into depth about what modular data centers are. This is mostly a theory question, which I think you will be able to answer directly if you looked at the videos of this week. Right? But so I won't mark this down. Right? It's okay. Let's just be that. So the following statements are correct about top of the rack in data center. So what is this TOR? Top of the rack. Okay. So this is basically about the design of a data center and what is expected in the design of the data center. So then what is the purpose of the leaf spine switches in a fat tree topology? Right? So there is something called, sorry, not the leaf spine, spine switches in Fat-Tree topology. So there are two dimensions of Fat-Tree topology: to connect servers to the network, to provide redundancy for the core switches. Is it to provide high-speed interconnection between pods, or is it to aggregate traffic from the edge switches? So one of those things is going to be answered. And then there are the following transport layer protocols specifically designed to address the TCP incast problem. Okay, TCP incast. Right. We'll take a short look at this, although it's not an easy problem to explain. So what is the primary purpose of a data center fabric? So fabric is not cloth here. It is a building block of the data center. So what is the purpose of it, right? So we'll take a look at that also. Just these are all just theory questions. And which of the following statements are incorrect about the end of the row in data center network? So there is something called TOR and there is something called end of the row. These are two different design ideologies, right, as to where they keep the switches. So which of these is incorrect about it? Right? So it's okay. Once let me share my screen. All right, we're good to go. So that is data center networking. There are these two topologies. And then there is this technical term called bisection bandwidth. And then there is also the top of the rack switch, which is going to tell you what the switch does and why it is placed on the top of the rack. What is a rack in the first place, the first point. And then there is this TCP incast probe. Let's slowly go through each one of these. But before all of that, I'll just give you a layman's introduction to why data center networks. So why data center networks? So right. So networks have always evolved out of need, right? So necessity is the mother of invention, right? Okay. Now the question is, you have a network in the house, in your own house. You have a network, right? And let's say you have a router, and you have a computer that's connected to the router physically, and you have uh, then you can make sure that it's connected by Wi-Fi to your mobile phone and all of that. So this is also a network, the home network, right? And probably what will you do? You'll ask for some Netflix movies or something like that. So you go through the internet, and then you reach the data center. So a data center is nothing but a location which contains many servers and it houses all the data for that particular company, right? So you go through multiple paths and then you finally reach here, you go to the data center. So now the question is the data center also created as similar to as home network? Um, or is it different, right? Right. The data center also I can have, of course, the router. I have a server and I'm connecting the server. I have another server, the server, the server, right? So what's the big deal, right? So why the huge noise around data center? Why is this the case? Right? So you can always connect every server to your router and you can say serve the data, right? Um, Also, by the way, what is a server? It is nothing but a high performance computer. That's all. It's just like a laptop or your Windows PC or your workstation. Workstation is also nothing but a slightly better personal computer with more compute, more RAM. But these servers, they are quite capable. Uh, so some servers that we have at IT Hyderabad here are pretty much having 128 GB of RAM. I'm not talking about raw. I'm not talking about hard disk space. I'm talking about RAM. So usually in mobile phones we have 8 GB of RAM or even 16 nowadays, right? So and in computers also we have laptops we have 32 at max. I think mostly 32 is you can upgrade to 54. So there are servers with 8 GB of RAM or even more. This is low end server. We have high end servers as well. Probably TBs of RAM as well. I'm not sure. So that is what a server is. Server is a high performance computer. So why does it need to be of high performance? Why because it needs to serve a lot of clients. As a clients, they are me, you, or whoever is requesting for some data from the server, which is in the data center, right? Needs to serve a lot of clients. Therefore, it needs to be capable enough to support multiple people trying to extract data from the server. Right. So with that out of the way, coming to the original question, what is so special about DC data centers? I'll give you a minute to think about it. So because we are speaking at the internet scale, right? So we are talking about supporting around millions of users simultaneously. Because we have to serve a lot of people, the margin for error is very less. So most probably in your own houses or in your own homes, when you're sending some packets, you generate a packet and then it goes here, and then most probably these delays would be in the order of milliseconds. But data centers have to operate so fast that they have to serve data within microseconds. Right? So the scale is different. Why is the scale different? Because so many people are requesting for data from the data center. Right? So for that, they tend to put this data center on a huge land area. Right? So these can also be called as godowns or warehouses. And all of these store large amounts. A house, large number of servers. And these servers are all interconnected. This is the second aspect. So which means, in other words, they are all networked. Which means that the servers can speak amongst themselves also. There's a point which will make sense later. Means speak amongst themselves. But why? We'll answer that question later. So basically, if you look at it, this is a quote directly from your lecture classes. Data centers are the supercomputers on which our day-to-day activities run. Beautifully said. Okay. So these data centers, right? They are facilitating and hosting hundreds and thousands of these servers, right? Around. See, they're serving millions of users, and the data centers contain around thousands of servers. There's pretty much more than 100K. K means 1,000, so 100K is like 1 lakh. So managing these many number of servers So managing these many number of servers is not an easy task. That's a lakh. They give you 10 computers, or even if you've noticed in your labs, you have about 40, 50 computers. Managing these 40, 50 computers takes pretty much a whole manpower. That is given, a lab in charge is given, and that lab in charge pretty much has to take care of all these computers. And if the lab in charge is, or rather the lab attendant or the lab uh, assistant is intelligent enough, he'll probably try to automate the lab computers using scripts which he can control from a single terminal, or he has to go and individually take care of things in all of these lab computers. So when your exams are approaching, they tend to uh, remove access to certain ports. All these things he has to do it manually. So managing even 40, 50 computers is no joke. But here in data centers, we are pretty much managing. And by the way, I'm saying we're managing, it is happening right now. The world runs on these data centers, and the the volume of traffic that is exchanged in these data centers are tremendous and huge. But in spite of all this, you are still getting your data, you're still getting your videos, you're still getting all of it. So this is pretty much modern marvel, in my opinion. Right? So basically, in a nutshell, data center is a facility that is used to house computer systems and associated components such as networking and storage systems. So as along with these network and storage systems, we also need cooling, right? So just having servers is not enough. These servers, because they are high capacity, generate a lot of heat, and this heat needs a cooling system. So basically, this is a complete warehouse, which is pretty much giving the utmost care to these servers, right? And of course, you also need to have uninterruptible power supplies. So when it comes to uninterruptible power supplies, just a small anecdote, not anecdote, experience. So I visit the data center from time to time. IIT Hyderabad. So it's a bit intimidating. You have these racks. You look at the formal structure later. Then you have one server like this, a server like this, server like this, server like this, and then on top you have the TOR, top of the rack switch, and the switch has multiple ports. Each of these ports is connected to one of these switches like this. It's very simplistic view. Don't assume this is how it is. So this is the top of the rack. So this is called the rack. Top of the rack. This is what you see from the front. If you take a look at the back, you will have redundant power supplies. So basically, each of these servers, right? This is server 1, server 2, server 3. And they have 2 power inputs. So these 2 power inputs are, because if one fails, the other one takes over. So basically, this was new to me when I went into the data center to see what is what. It appears that you have 2 inputs. Because in most appliances that we buy in the house, or if any computer also you have one input power, right? So you connect the power cable and then you switch it on. But the servers, they have 2. So essentially, they are built keeping in mind the sensitive nature of the activities that they're going to perform, right? And which is also pretty much why they're very costly. It does not make sense for you to get a data center, what do you call? I mean, get a data center based server and put it on your house. You'll probably end up spending more than the amount in time to cool it. Right? So data center typically houses a large number of heterogeneous networked computer systems. So it also houses large number of heterogeneous networked computer systems. Right? So what is this heterogeneous? Heterogeneous means they're not the same. What I mean is, this is the data center. These are some machines. Let's say these are all from HP. These are some other machines. These are all from Dell, EMC, or multiple such vendors exist, right? So all of these different heterogeneous, different types of servers are to be networked together, right? Although this is not that much of a problem, because we have standards, we have Ethernet standards, which allow data transfer irrespective of who the vendor is. Also, in terms of remote automation, most of these vendors are on the same platform. Hence, you can look for management also through common. What I mean by that is you want to control everything, right, from a single point of central point. you will be able to. So mostly this challenge is not there, at least in this area, right? So it's basically an entire building. So if you go through the video, the lecture videos, you'll see that you have racks and racks of storage. So it would be interesting to take a look. There's a video on YouTube called "Look in View into Google's Data Centers." That is a very interesting video. They take you inside the data center and let you know what is there, what is not there, right? So now let's look at some types of data centers. First one is enterprise. Second is specialized. Third is co-location, let's say. And then what is cloud, right? So enterprise data centers. So these are all owned and utilized by companies for their own internal computing needs. Um, they are they could be built by custom hardware also. It is internal, right? So if I'm only going to communicate internally, then I can build my own custom hardware. I can create my own uh, network to suit my need. I don't have to worry about the outside world, because as long as it's able to communicate with its own internal nodes, it should not be a problem. So then these are all also custom built to meet the requirements of the organizations who own them and are housed on premises. So these specialized data centers, so they are all built for one huge application. In the application, you have SP, you have Google, and you have all these big conglomerates who have a data center of their own, huge data centers. And you have co-location data centers where if I have money, I'll buy servers and create DCs and rent it to people, right? And here by rent, I mean I'll totally say for this amount of time you have complete control over the data center, top to bottom, right? And that is what these co-location data centers are. And finally, you have cloud. Cloud is also very similar to these managed and co-located data centers, but they don't give you complete access over the whole hardware and everything. So here you have things like Amazon EC2, and then Azure, and then you also have some smaller uh, companies like Heroku. So basically, they give you a part of that hardware of the server. Right? They have multiple ways of getting only parts. So these are all different types of data centers. And if you want to see data centers with more than 100K servers, 1 lakh servers, you have Microsoft, you have Facebook, you have Google, and we also have new data centers coming up in India. Hyderabad is going to be the host to, I think, Google data center in the future. They have planned to build their data center here. It's going to be huge, right? And what we have to realize is these things are very big. So look at the numbers. This is from your video only. Google has around 100 billion searches per month. Meta or Facebook has total of 1.15 billion. That's not a million, that's a billion, right? And then you have Amazon with around 120 million users. So what does all of these things entail? I'm repeating these things because just to give you the idea of the scale at which we are dealing. So all these things translate to around um, you have a typical data center, you have like 10 to 100K servers, and then you have petabytes of storage and hundreds of terabits per second of bandwidth. And funny enough, these data centers, they consume around 1 to 2% of global energy consumption. And of course, a lot of money, right? Then you have an example that was described in the classroom, I think, where you do web search and beautiful example is shown. And if you want to look at data centers in India, we have multiple places. Highest number of data centers are in Mumbai, Hyderabad, and Bangalore. Right. So Bangalore has around 28, Mumbai has around 23, Hyderabad has around 12. So we can understand why these are all the uh, certain capitals of India, right? So Mumbai has 23. Mumbai is not known for its IT, right? But it still has 23. The reason is it's the financial capital of India. So finance is equivalent to stocks, and many financial organizations are there, which all rely on networks, computers for their transactions and for their trading as well. So you can see a lot of people setting up their data centers in Mumbai, and we also have it in Chennai, but it's not anywhere comparable to Bangalore. It's 28. Bangalore is the IT, the Silicon Valley of India, right? Right. So these data center requirements are growing exponentially. Right? With the increased number of citizens who are going online, and India also launching the Digital India initiatives, uh, there is a huge requirement of data storage. So we have a national data center. It's located at Delhi, Pune, Hyderabad, Bhubaneswar, and Chandigarh. And there's in Indian government's own data center infrastructure. Right. So some of the there is one more I think, more fact, or rather no interesting fact is there is a Microsoft data center, right? So if you do look at this, the land area that these data centers occupy, the highest is Microsoft, is located at Chicago, and it has around 7 lakh square feet. So since they won't be able to understand this in relative terms, you have a big cricket ground, and that cricket ground is going to be around 2.4 lakh square. Right. Yeah, so just to give you the idea of how big these things can really get. So there is also something called um, we have a we have a nomenclature, but if you but among this nomenclature, what seems to have been asked in the questions are uh, container data centers. Right? So, okay, I'll write this also. It's asked in the questions. We have macro DCs, macro DCs, nano DCs, and container DCs. So simply put, macro, large, right? It has 100K, greater than 100K servers, and micro is say 100, sorry, 1,000 or more, greater than 1,000 servers. Okay. And nano is even smaller than that. Now, coming to container data centers, right? So this is even smaller, less than that, less than 1,000. This is called modular data centers. So these container data centers or modular data centers, right? It actually does mean what it says. The data center is housed inside a container, right? A container is what? Have you seen those huge ships which contain just boxes and boxes and boxes, containers, right? Imagine if you take one of those boxes, it's a container, and if you fill it with servers, right? And then you have ports to plug into, and you can move this container around. Right? So these are all sold as a bunch in the bundle. And the reason why this is popular is because if one company decides to buy uh, equipment for data center, they don't have to buy these equipment separately and set it up. They get this container and then they deploy it on the premises. And if they're shifting, if they're moving somewhere else, they can take it and then they go somewhere else. So essentially, the plus points are speed of deployment and high mobility. You can move, and that's why it is big. And I think in the video you would have seen some examples of these container data centers. They have fans behind and multiple different types, but it essentially looks like a, a metal box, right? And essentially they vary, but in a sense, I think they have around 30 petabytes of storage. So petabytes is like more than TB, right? So, gigabyte, terabyte, petabyte, right? And nano, nano is just uh, less than 1,000, but to be more accurate, it is pretty much like a P2P network. All these nodes communicate with each other, right? Um, let's not go into nano data centers right now. Okay. Okay. So I think I've covered what a server is and what a rack, right? Probably you might have seen the videos as well, where there are beautiful um, images that can help you visualize these racks. That probably will do a better job than what I can ever do. Right. So what are the components in a data center? First is air conditioning, right? And then you have fire protection. You have, of course, monitoring systems. And you also have devices that repel rodents. Basically, it emits rodents in the sense rats and all of these creatures. They cannot live inside the data center. The reason is there is constant electromagnetic wave that is being emitted by these rodent repellers, and there is essentially a lot of such components to make sure that nothing goes wrong inside. So it's a very complex, very sensitive thing, right? So now coming to what are all the challenges, right? Four challenges. So important. So one is scaling. So scaling in the sense you should be able to support a large number of clients. Rather, you should be able to expand, right? Second is performance. So you can't buy a lot of equipment and keep and only extract performance from only one subset of. You have four servers. Does not mean that you only overtax these two and let these two go free. So there are things like load balancing and networking as well. And there are these aspects which are definitely a challenge because you're scaling to a large number of people and you're you're trying to manage near about trying to manage a large number of these systems. So that's why performance is another challenge. It's not easy. And then of course there is obviously power. We previously saw it 1 to 2% of global power consumption goes to data centers. It's only going to increase in the future. Essentially, you want to minimize carbon footprint. Right? And some slightly lesser known challenges to the outside world. To the research world, these are more important. But yeah, so fault isolation and failure resiliency. So, what is this fault isolation? You have n number of servers like this, say, and if one of these servers goes down, then you should be able to exactly find where the fault occurred. This might seem simple when you look at a diagram, but if you're now operating at a scale of 100K servers and one of them starts malfunctioning, so how will you find out where the problem is, or rather, how long will it take for you to find out where the problem is? Right? So this is the challenge. Finally, failure resiliency, or this is also called fault tolerance, where in spite of failures, the data center should work fine. But how is this possible? A trivia question. I have a video about a cat. And this video inside server 1, and there are 2 servers. Sorry, 3 servers, let's see. It's a simple data center. I am requesting for cat video or dog. I told you're a dog person, right? Now suddenly what happened? This link got destroyed, but the cat video is inside this. So is this fault tolerant? There is no, because once this link goes down or something happens to this host is down. Sorry, the server. So once this server is down, then it is pretty much impossible to access the cat or dog video. So how do you give fault tolerance? How is it possible? How can they give fault tolerance? Right. So you can type your answers in chat if you want to. Not also, it's fine. I'll give you a minute to think. Let's get some water. Right. So how do we provide fault tolerance? Simple. We replicate the same in the other servers. But now comes another question. If you replicate the same video in the other two servers, then what happens if I change something in this video? Okay, let's not take the example of a video. Let us take the example of a file. If I change something, what will happen? If I change something here, then this will be updated, right? And these things will be remaining with the old version. So essentially, in a data center, once an update occurs, then it has to be migrated or it has to be reflected in the other nodes or other servers. I'm using the word nodes and other servers interchangeable, right? So these other nodes should also have the updated value, updated file, or updated video. Therefore, in the data center, we have two different types of traffic. Yes, north-south. One is east, west, right? So this is the data center, and we'll come to this topology later. Probably in the previous problem-solving session, you would have attended the way this data centers are organized, right? So probably you can refer that video, but I'm not going too deep into it right now. So these are all the servers, right? At the bottom, the leaf nodes are all the servers. So if I need to update something between these servers which contain the same data, then I need to send traffic like this and update it. Right? So this is why there are two types of traffic in a data center. One is traffic that comes from the outside to the border router, which then fetches data, puts data, and once it puts some data or updates some data, there is an east-west traffic that um, occurs only inside the data center, right? These updates. So unfortunately, to give fault tolerance, we are having to do all of these redundancy. We're doing fault tolerance at the expense of the expense of memory and bandwidth. Why bandwidth? Because you have to allocate bandwidth, have to take into account that east-west communication is also going to occur. All right. So I think this would be the introduction to data center networks. We can probably go into the questions now. I think there was one more word called fabric, right? I think we'll cross it when we come to that. Right. So a typical data center network. Right? contains border routers. So these are all the, so this is the data center. This room is the data center. Then this is the internet, right? So these are at the edge of the data center. So they establish or enable connections outside the data center. And then you have topologies like this. Have switches. And then you also have another layer of switches. So these are called tier 1, tier 2. And when I say switch, I mean router. But in data center or in most contexts nowadays, it's called a switch. Do not confuse that with just the layer 2 switch that is conventionally taught. And then the servers are connected to the leaf. They're always the leaf node, right? And each of this, okay, it's a rack, and then here you have the top of the rack switch, TOR switch. We saw what a TOR was, right? And that's connected to each of the servers in the rack. So this is a rack. So you have multiple racks like this. And so on. So basically, the point is, by the way, all of these things are interconnected in all possible fashions, that is, right? And also, one more terminology that you might come across is that this can also be considered a pod, a POD, right? Anyway, so but of course, these are all connected over off top as well. Why multiple connections? It's because you want to have fault tolerance and redundancy as well, right? So there was one more word there called end of the row architecture. So I'm just going with respect to the questions. So architecture and end of row. So we saw what a Tor architecture is. Tor is, we have racks. Okay. Tor switch. This is server 1, server 2, server 3, server 4, 6. Another rack like this, another rack like this. And all of these are connected to the next switch, which can also be called as the aggregation switch or the tier 2 switch. But in an end of the rack architecture, each of these servers, right? Each of these servers have a connection with the aggregation switch, or this is also called as the network access so very raw. We have server 1, 2, 3, 4 here. 1, 2, 3. So and you have the aggregation switch, right? This is also connected. This is also connected. This is also connected. Also connected. So essentially, there is a direct connection between all of these servers and the switch. So thereby reducing one level of what we call complexity. But this is also not the you have zero use case dependent. We don't know which is best and which is not best. And of course, TOR is called interact assign. Why is it called interact assign? It is called interact design because you have a switch inside the rack or rather on the top of the rack. Right. So if you compare these two, I think there is a comparison on the official video. You will get to know that there are advantages, there are disadvantages as well. Right. So now, yeah, now it's time to go into the questions. Pretty much that's what there is to talk about data centers. And okay, let me just copy the questions and we'll proceed with that. Just copy the one moment. Okay. Questions. Just wait for question number 9 to come. Okay. So I will look at these questions. Let us try and some of these terminologies. All right. So which are the following? Which of the following is not a typical component of a data center network? Is it servers? Is it network? Or is it storage? Or is it workstations? Data center network definitely does have servers, right? Servers. Of course, this is not going to be the answer because it's not a typical component. So do we have network? Yes, of course, we have so much of networking equipment there. Is also not the answer. Storage, yes, of course, we're going to have storage. Storage would mean just machines that contain so much of data. Sorry, so much of hard disk capacity, right? The only work that that machine would be able to do is store information and retrieve information. It might not have an operating system of its own. It's different from a server. Keep that in mind. And workstations are smaller computers, so we don't see them in data centers, right? So the answer is D. So what is the total number of servers supported by 4-port switches in the leaf spine topology? Spine topology. Yes. So for an example for a spine topology, so probably it will be good to learn about that. So as the name indicates, there are leaves and spines. Just take it as it is. There is a leaf and there is a spine, right? So an example probably look like this, right? In a very simple way, have spine switches, spine switch. This is spine switch 1, spine switch 2, and then you have leaf switch 1, leaf switch 2, leaf switch 3. And then of course the leaf switches will contain the end devices, which is nothing but the servers. Right. Now we are in a lot of ways concerned with the number of servers that can be supported by 4-port switches in a leaf spine topology. So basically, all of these switches contain 4 ports. In the sense, you can have 1, 2, 3, 4 connections. So what can be the total number of servers supported? Let us try to make a diagram, right? If we make a diagram, uh, we'll come up, so answer is given by a formula, but let's verify the formula as well. So the answer is given by a formula E cube divided by 4. This K is number of ports. So this will basically be 4 cube by 4, which is equivalent to 4 square, which is equal to 16. So 16 is the answer. But why is it 16? Let's take a look. Right. So if it is 16, then you should basically be having 3, 4, 6, 8 servers, and 10, 11, 12. One second. Right. So the direct answer to this question is 16. You can just plug it into the formula. But I wanted to visualize this for you. Maybe I'll visualize this in next class. But for any such questions, you just need to plug it into the formula k cube by 4, and you will get the answer as 16 servers. Similarly, which of the following statements are correct about factory topology? So factory topology is a predecessor of leaf spine topology, where it has identical bisection band. So what is this bisection bandwidth? Is the question, right? We'll look at that. And factory also has same. Right, so A and B are correct. Let's go through all the questions and come back to question number 2 and 3. Right? And then we have time. Let's solve it. So which of the following statements is/are correct about modular data centers? So we saw what modular data centers are. So they are highly mobile. Yes. They have a high operational cost. No, that's what they were built for. The operational cost is less. So of course they have lower operational costs and faster deployment. So A, B, and C. So which of the following statements are correct about top of the rack switch in data center network? So we saw what a top of the rack switch is and where it's kept. It's kept on top of the rack. And what does the rack contain? The rack contains mini servers. We also call them blade servers. Now let's see. A data center design where all servers are connected to a single switch is not TOR. This is EOR. Correct. It's end of the rack. This is not. Core switches are typically used as TOR switches in the data center. No. Core switches are different. TOR switches are different. Core switches are at the topmost. Topmost in the sense they are in the top like this. These are core, or rather these are core. It depends. Depending on the number of layers. And these are all leaf switches, and then you have the racks out of which you have TOR switches. So coming back, a network architecture where switches are placed at the top of a server rack. True. It's very clear, it's true. Networking technology of wireless communication in data centers. Absolutely not. There is no wireless communication in the data center. It's all wired. Keep this in mind. It is all wired. Why do we need to go to wireless when we have a whole building just to ourselves, right? So wireless always gives less bandwidth than wired. So the answer is C. What is the purpose of spine switches in a flat tree topology? So we saw a spine, right? So I think you have leaf switches like this, and then you have spine switches. So the main purpose of these spine switches is to enable east-west traffic. Of course, any traffic that is coming from outside is also allowed by these spine switches. But if one pod, let's say one pod here, wants to communicate with another pod over here, then it has to go through the spine switch. So essentially, it is to provide high-speed interconnection between pods. So if you feel these are correct, I'll tell you why these are not correct. To connect servers to the network. Um, they are, in a way, yes, but it is not specific to this. So any switch, if you take, is applicable for any switch, not specific to spine switches. So better not choose such vague answers. Provide redundancy for the core switches. So core switches are over here, and you want to provide redundancy for them. No, there is no redundancy for them over there. Once these are lost, it's pretty much gone. So that's also not the case. And then third is correct, C is correct. Then D, to aggregate traffic from the edge switches. Um, it doesn't aggregate traffic, it passes on the traffic. So these are also called as the edge switches, top ones. So it doesn't aggregate anything over there. It in fact disaggregates it. So whatever comes here, it splits it into multiple other directions and then it's over that direction. Right? So now, which of the following transport layer protocols specifically designed to address the TCP incast problem? Right? So what is this TCP incast problem? This might be a bit difficult to understand, but nevertheless, let me try to answer it. Play this. Right? The answer is DCTCP. The famous paper came out which addresses this incast problem. So this has something to do with the switch network buffer. In a sense, the buffer or the queues, right? They fill up, and these buffers are of course TCP buffers are full. So you have a TCP buffer here. This buffer is full, but the sender is keeping on sending packets without knowing that the buffer is full. The reason why this is a big problem is in data center networks, you have microsecond communication latencies. So by the time these packets are dropped and timeout occurs, and then the sender understands that the timeout, of course, and then it resends the packet. There's a lot of time that is wasted, right? And the time that is lost, right? It's very valuable in a data center environment. And this is more so ever more evident with short flows. I know I'm going into a lot of technicalities here. Short flows are small communications with very less number of packets. So by the time the flow or the sender understands that there is a problem with the buffer, it would have sent all the packets by that point of time. So pretty much all the packets have to be resent. There's also a lot more technicality. So TCTCP is basically the answer to this. So the other ones are all other protocols which you might take a look at if you're interested. So then what is the primary purpose of a data center fabric? So a fabric, as we call it, is nothing but this is the fabric and this is the So it is to provide a high-speed backbone network. So this is the backbone. So the network fabric is nothing but the backbone. It is not cloth. It is called a fabric because it's woven together through links with links, and that's why. And of course, this is not the case. This is also not the case. Not the case. To place it at the top of the server rack, no, doesn't do that. To manage power and cooling within the data center, nope, not really. And to provide storage for data centers applications, that is also not the case. So the following statements are incorrect about the end of the row in data center networking. End of row. So you are sorry, is incorrect. Okay, these are incorrect. End of the rack design helps. So what happens in end of the rack? The individual servers in the rack are connected to the aggregation switch. Right. So the endo of the rack design helps decrease the number of switching devices. Yes, because you don't need a top of the rack switch in all the racks, right? So number of switches decreases. This is true, which means it's not the answer. Requires smaller cables from servers to switch as compared to TOR. It requires longer cables, right? From server to switch as compared to TOR because your number of cablings also increase. You are individually connecting every server to the switch. This is wrong. Lower rack space and cooling power. Yes, there is a lower rack space because you don't have an extra TOR. The switching equipment generates a lot of heat. It's also true. For servers in the same rack, layer 2 traffic efficiency in end of the rack is lower than TOR. Um, layer 2 traffic efficiency. Right. So what they mean by layer 2 traffic? Layer 2 traffic is nothing but MAC based routing. So what they mean is if this server has to communicate with this server, it basically has to go all the way to the aggregate switch and then come back. But if there is a TOR, it only has to go to the TOR and come back. So layer 2 traffic, which is routed based on MAC address, is more efficient in TOR than EOR. So TOR is better in that case. This is what it's saying that the efficiency of EOR is lower. So this is also correct. Which means right now I actually want to show interactive example of if I can open it up right now. Not lost it. If I can, I'll show you. Otherwise, in the next class, I will show you. probably we'll cover this in the next class. I think that's the end of today's class. I'll give a short introduction to this in the next class, because next class is also going to be on data center networks. We'll probably look at the protocols that are required, and show you an interactive demo of leaf spine architecture and stack tree topology as well, to grasp it properly. Knowing it is not going to be as effective. So thank you. You can probably leave a call.